Hello, welcome to your presentation on the track of Research and Development, a Global View. Tsinghua University has contributed to the development of Chinese DTMB standard and the promotion worldwide. Today, Dr. Jian Song, professor at the Department of Electronic Engineering from Tsinghua University in China, will present his research about efficient sliding window decoding of specially coupled LDPC codes for broadcasting.
Hello everyone, this is Jian Song from Tsinghua University. It is my great honor to be invited again to join this super event. Last year, I have physically attended and reported our work on specially coupled LDPC, which is short for SC-LDPC. We believe it is suitable for broadcasting systems, and my presentation was mainly on the code design. Today, we're going to introduce our latest work on this SC-LDPC decoding, and the title of my presentation is Efficient Sliding Window Decoding of Specially Coupled LDPC Codes for Broadcasting. The collaborator of this work are my colleagues, Professor Ke Peng, and two of my PhD students, He Zhitong and Zhang Yushu. Within 10 minutes, I'm going to highlight our recent work. The presentation will be divided into two parts. In the first part, I will briefly introduce the background of our work. SC-LDPC code is a new class of LDPC codes with convolutional structure and the mathematical characterization. The illustrative figure is shown on this slide. Typically, LDPC codes are terminated at both ends, so we can treat them as the block codes, while SC-LDPC is still block code, yet possesses the convolutional structure. Therefore, certain property from convolutional codes through this special coupling. The most important property of this SC-LDPC codes is the universally capacity approaching capability over most of the channels. And this is proven in literature 1. In other words, SC-LDPC codes are suitable to deal with various transmission scenarios. Thus, it has a great potential to be applied to future broadcasting networks. Sliding window decoding is an important decoding algorithm for SC-LDPC codes and was first proposed in literature 2 by taking advantage of the inherent special coupling structure of SC-LDPC codes. Using this scheme, it only decodes a portion of SC channel graph called a window for one iteration, as shown in this figure. While the decoding in the window is completed, we will move to the next window and repeatedly perform this operation until the decoding of all the windows are finished. It is straightforward that the decoding algorithm could greatly reduce the decoding complexity and the latency as well to fulfill the high throughput and low latency requirement for future broadcasting systems. I will now introduce the details for our sliding window decoding scheme. Based on the quasi-cyclic structure, we treat Z rows as a layer shown on this slide and use layer decoding scheme. Each window consists of NW consecutive layers of check nodes and all the related variable nodes. Here, NW is called the window size. We also consider the boundary conditions. That is, because the SC-LDPC codes are terminated at both ends, the window that consists of the starting layer or the end layer may have less than NW layers. To compare sliding window decoding and conventional full BP decoding for SC-LDPC codes fairly, we define the decoding complexity for sliding window decoding on this slide. Here, MSC is the total number of rows, and IJ is the number of horizontal processing operations for row J. The decoding complexity is defined here as the average number of horizontal processing operations for all the rows. Because the horizontal processing is a major part of the LDPC BP decoding process, the decoding complexity we define here can represent the number of horizontal operations in the actual implementations. And the memory for actual implementation is proportional to the product of the window size and the subcoding length. In the second part of my presentation, I will show the contributions of our recent work. First, we check the impact of NW on the decoding performance. It shows that for SC-LDPC code with a true rate of about 2/3 and the length of 92,000, NW equals to 16 is seen as the appropriate window size when the decoding complexity ranges from 30 to 60. As shown on the right figure of this slide, we assume that the bi-AWGN channel with QPSK modulation is used with the bit error rate ratio set to 10 to the power of -5. Now we can evaluate the impact of our proposed sliding window decoding algorithm with the early determination, which is short for ET. Here the window size is set to 16 and the maximum iteration number Imax within one window is 2, which equals to the n number of iterations divided by NW. The conventional sliding window decoding applies to the same number of iterations to each window as a benchmark, while sliding window decoding with ET helps reducing the overall number of iterations. And there are two proposals on the ET. One proposal stops the decoding iterations within the current window earlier, while the proposal 2 can determine the entire decoding earlier or decides to slide to the next window after the current window decoding is done, regardless of whether early determination is applied to this window. ET criteria we chose here is parity check based, and we will move to the next window if the parity check equations of the first 3 layers are satisfied consecutively several times. This is our simulation results for the sliding window decoding with ET. The left figure shows that the normalized iterations needed for these 2 different ET proposals within the signal-to-noise ratio range of our interest, and also using the complexity for the conventional sliding window decoding as a benchmark. It is seen that the proposal 2 uses far less iterations than proposal 1, since it uses ET to reduce the normalized iterations when SNR is low, and the result of the right figure shows that the sliding window decoding reduces decoding complexity greatly with a slight SNR loss compared to the conventional full BP decoding, and the gap is about 0.1 dB. And the gap between the ET algorithm and the conventional sliding window decoding algorithm without ET is around 0.02 dB. Since there is no non-negligible difference between these 2 ET proposals, apparently ET2 is highly preferred due to its low complexity. Based on this very brief introduction, we can conclude our work in the following. The first one is our proposed sliding window decoding method could greatly reduce the decoding complexity of these SC-LDPC codes with slight SNR loss. And it might be difficult to directly extend this scheme to the other LDPC codes because of this unique structure of this SC-LDPC code. So therefore, certain modifications are needed if we want to extend our work to the other type of LDPC code. With that, I conclude my presentation, and thank you so much for your listening. Hopefully, in the future, we can have the physical meeting next year so that I can share more our work with you on this SC-LDPC code for the broadcasting systems. Thank you again.
Professor Song, thank you for your time to share your researches with us. Thank you for watching our presentation. If you have any question for our speaker, contact him through his email address. I hope to see you in the next episode of Research and Development, A Global View.